at how in thresholding we are literally just labeling pixel values based on whether they're above or below a threshold. And this works well in CT scans because the grey values are dependent on a very fairly simple physical property, that being the transmission of X-rays through a tissue. But images such as MR scans have a very much more complicated intensity distribution based on a whole range of factors that we won't go into. So I just wanted to show some problems here and a few more algorithms. So for example, if we go back to our MITK workbench shown here and we load up that MRI scan. Firstly, if you look at this scan, you can see where my mouse is on the axial slice towards the back of the brain. It's kind of mysteriously or abnormally brighter than the surrounding area. So the same tissue type at the back of the brain could be 1 pixel value. So for example, here it's 600 odd, but towards the front of the brain, the same white matter tissue is 448. So this makes, having things like intensity in homogeneity across the image will cause problems, as will simply having overlapping intensity ranges for the different tissues you're interested in. So that the problems when you actually come to do segmentation on real life examples is that the range of intensities are simply not that easy to get hold of with thresholding. So if I imagine I start a new segmentation now, I mean, let's just play with the thresholds. For example, you just can't, for example, extract grey matter. So if I zoom in a bit, the grey matter around the brain is this layer of kind of mid-grey, not this brighter grey in the middle, or not the black next to it, this kind of mid-grey piece. And almost regardless of what you do, you can't find with simple thresholding a range of values which picks out the tissue type that you want. So you kind of give up with thresholding, which means you could then try something different. So the next most complicated thing over thresholding or OTSU thresholding, for example, is region growing. Now, I don't know all of the controls here, but essentially the purpose of region growing is you actually nominate a starting point of a seed. So if I click in this region here on the axial slice, I've placed this little seed in yellow. And if you imagine that you've just picked a pixel and you say, this is the thing I'm looking for, this is the part of the brain that I want to segment, what you then do is iteratively move outwards looking at connected pixels. So you can look in a 2-dimensional or a 3-dimensional neighborhood. You can look at, for example, up, down, left, right, front, back. So the 6 connected neighborhood or the 27 connected neighborhood if you include diagonals. And you add to the segmentation if you're within a threshold range. So if you look over here on the right hand side, I don't know where these numbers came from, but see this lower threshold is 434 and the upper threshold is 774. Let's make it a bit, so we know this white value round about here is about 600. So let's make this 500 and let's make this 700. And you say run segmentation. Ooh, and it tells me that my specific seed point, let me have a quick check. Where's my pixel values? Hold on, I'll turn off these things here. Okay, pixel ranges round about here are ballpark 500. Right, let's go back and try that again. Make sure we don't have too many spare images. Let's create a new segmentation and let's click on region growing. Let's place a seed here. It's about 500. So let's not tweak these too much. Let's go from between 490 and 700 ish. 700. If we now run segmentation, what you can see has happened, and you could argue not a lot, pixels have been added to the current segmentation by spreading outwards from that seed point and including things that are connected and within those intensity ranges. That's the general idea of region growing. You start at a seed point and you move outwards, adding connected pixels as long as they are within a range. If I'm honest, this slider here, adapt region growing, don't really know what it's doing. It's probably adding a range of values. It's obviously doing some kind of additional range of threshold values. But as you can see, it gives you a way of defining how to add pixels automatically, but it very much depends on, again, the data that's surrounding. So I would expect this to work quite well if I was looking at vessels within contrast enhanced vessels within a liver, for example, because you could grow your region along the vessels. Note, however, that if I pick another seed and rerun the segmentation, this thing is only giving me one seed point and it's growing outwards from that point. And it grows outwards in 3D based on these range of values. But this is a weird image, and that's the reason I chose it, because the range of intensities for the given tissue type is a bit too variable. It's basically the imaging type itself is not very clearly defined. Basically, there's too much intensity variation across the image. So region growing is simply adding a pixel if it is A, connected, and B, within an intensity range. Another common algorithm in this kind of region, or and if we're looking at evolutionary or iterative algorithms, another common one is called fast marching. If you imagine you start at a seed point, so it's a bit like region growing. Imagine you start at a seed point, but imagine you're blowing up a balloon. So a balloon has a specific surface and it evolves outwards as you inflate a balloon. But if you also imagine, a balloon is made of some kind of latex or rubber, which has a constant stiffness, which is why when you blow the balloon out, it comes roughly spherical. With a fast marching algorithm, you can say, well, imagine I've got a surface that's evolving outwards, but I control the stiffness of the surface and how fast it grows outwards. You can imagine that it spreads outwards like a balloon expanding. But if you control the stiffness, it will then eventually evolve itself into all the kind of nooks and crannies as it iterates outwards, looking for pixels that are within a range. Because you can control the stiffness of this balloon or this surface, it will tend to produce smoother edges, and it will stop when the intensity values are kind of too convoluted, because a stiff balloon won't iterate into those areas. So let's try and give it an example. If I click on this fast marching thing, if I add a seed here, this thing does then take a bit of processing power. It runs away there. I'm just using the default parameters. You can see it's been. Do you see how it's kind of iterated outwards, and it is then trying to follow the contours and keep itself as a sort of more connected surface. Let's see if we can work out what sigma is doing. I suspect this could be a slow process. Hard to tell because it's updating so slowly. Well, it hasn't crashed yet, which is great. Threshold -1 and 2000, stopping value 2000. And the stopping value just tells you this is the stopping value. So we know that those intensity values of the white matter are probably up to about 700. Ooh. But it's a bit slow for when I type 700, the 2 zeros. Here we go. And let's go minus 450. So here you can see how this kind of surface has evolved outwards from the seed point, which interestingly I seem to have cut the threshold off. Let's put this back to 0. So it evolves outwards, and you can see in this axial window that it hasn't gone all the way to the edge of the white matter, presumably because there's a limit on how bendy this surface can be. But I hope you give this an idea of what a region growing or a surface fast marching algorithm looks like. In practice though, your success at producing a segmentation is always going to be limited by how well is the intensity range in the image, how unique is it, and how easy is it to extract from all the things that are around it. If I now go confirm segmentation and say I'm happy with that, in practice, imagine I was trying to extract some part of the brain. In practice, you still nearly always end up with things that need manually editing. So I'll quickly go on in the next video to talk about some manual editing tools.